this chapter, we are going to see a very powerful mathematical technique called mathematical induction. We use MI as an abbreviation. In each mathematical induction question, there should be a proposition, or simply you can state we have a statement. And now we are going to see or to prove why it is true. For example, I told you that the sum of the following numbers 1 plus 3 plus 5 plus up to, that means we are adding up all the positive odd numbers, odd integers, until the last one, which is called 2n minus 1. And I told you that the sum is n squared. Do you trust it? And now one of the way is you try to substitute some numbers to check whether it's true or not. For example, you want to check 1 plus 3. In this case, 3 will be 2 times 2 minus 1, so that's why your n will be at 2. And on the right hand side, you have 2 square. 1 plus 3 is 4, 2 square is 4, so that's why it's correct. And then next, you try to check some more numbers like 1 plus 3 plus 5, where the 5 is 2 times 3 minus 1. That means there are 3 numbers. On the right hand side, you check for 3 square. Okay, 135 is 9, 3 square is 9, so it is also correct. You check for some more numbers like 1357, where 7 is 2 times 4 minus 1, and it's 4, which is 4 squared. 1 plus 3 plus 5 plus 7, total is 16, 4 square, which is correct. And then you can continue to check it one by one, but you find that you're only checking finite numbers. What does that mean? For example, addition to 7 is correct, additional to 9 is correct, additional to 11 is correct, so and so. But you can't tell me that it should be true for any positive integers n, which is given in the formula. So in this situation, we need the technique of MI to prove it. And so the idea would be, now we call this one as a proposition, and then we use the notation Pn to stand for it. What exactly you're doing right now would be, when you are testing 1 plus 3, you are talking about the statement called P2 because you are having n to be 2. If you go backward, so actually we missed the proposition 1, which is called 1 number only. The other side is 1 squared, and then which is also correct. And then in this situation, actually what we have been doing here will be we check for P1, statement 1 is correct, P2, P3, P4, the statements are correct. But we can't say the whole statement Pn. What values of n we take, it should be correct. So we come to the idea of mathematical induction here. The situation will be it will be like this. So first of all, the first step, we try to prove that P1 is correct. So it is our starting point, and normally it will be a very easy calculation. And then the second step is we try to assume at certain stage Pk is correct for some positive integers k. And then next we want to prove, and then we're going to prove the next statement Pk plus 1 is also correct. So the main point of mathematical induction is in this the way how we use the MI, we want to say that regardless of the exact value of k, whenever we have Pk is correct, Pk plus 1 is correct. So as a result, what the effect of combining these two statements, and then we take a look. So in this proposition Pn, actually we are having a lot of statements like P1, P2, P3, P4, P5, and then so and so. So there are lots of statements over there. And now, so the first statement is telling us that P1 is correct. So that's good. We have a very good starting point. Afterward, and then when we are going to the step number 2, when we assume Pk is correct, we can prove that Pk plus 1 is correct. What does that mean? That means if P1 is correct, P2 is also correct, when P2 is correct, P3 is also correct, P3 is correct, P4 is also correct, P4 is correct, so that's why P5 is also correct, and so and so. So as a result, by this linkage or kind of like domino effect that you can find some videos in YouTube, and then so the construction of the MI having the starting point P1 is correct, assuming PK, and we prove that PK plus 1 is correct, so it makes up a link that we can say P1, P2, P3, P4, P5, and so on and so forth, all the statements are correct. So that's enough to say that Pn is true for whatever, for all positive integers n. After understanding the principle of the mathematical induction, and then we come to take a look on what should be the format, how we can present the mathematical induction statement properly. And then so there are several bodies you can take it as a look. The first step will be we need to let the proposition, and then which is called, we let Pn be the proposition of, we have the numbers 1, 3, 5 up to 2n minus 1, which is equal to n squared. So this statement, it should be true for all positive integers n. So this is the first body. Okay, so you can say step 1. Next, we want to prove P1 is true. So that's why it comes to step 2, when n is 1. We do the calculation like checking the left and the right. When n is 1, there is only one number on the left hand side. So that's all, no calculation. While on the right hand side, and you should put n to be 1 because the formula is n squared here. And that's why it's 1 squared is equal to 1, which is equal to left hand side. So in this situation, we can say P1 is true. Very easy, right? So the main job for you is to understand the principle first, and the format will be your next job. Step 3, now we assume PK is true for some positive integers n. We don't particularly look at a certain value of k, but for any kind or any number of positive integers k, and then we are going to prove the following. And then next, we will go to look at the next statement when n is k plus 1. Okay, when n is k plus 1, and the left hand side now becomes 1, 3, 5. So it's better for you to still write the previous last term is 2n minus 1, but because now we are talking about k, so it's 2k minus 1. When n is k plus 1, there should be one more term called 2 times k plus 1 minus 1 over there. If you write that it's explicitly, and you have 135 up, adding up to 2k minus 1, and finally 2k minus 3. So this is the proposition or the statement we are considering. And now we have some ideas or some techniques when you deal with an MI question. First of all, when you assume PK is true, that means you should have a certain formula to apply. So as a result, that means PK, that means is 135 up to 2k minus 1, which is the last term. According to this formula, so it's equal to k squared. So that's why in your body, then the almost first a number of terms by the assumption it is equal to k squared. So in your work, we will say this is by assumption because you assume PK is true. That means you know the sum of these numbers from 1 to 2k minus 1 is equal to k squared. Next job we are considering k plus 1, PK plus 1, and what is your aim? it's better for you to write in a rough worksheet as a reference for when you are doing the job. So it helps you to be focused and you have an aim to prove something. The aim now will be, if we consider n is k plus 1, that means it's 135 up to 2k minus 1 and 2k plus 1. Oh, sorry, I think I make a mistake here. It should be 2k plus 1. And now according to this formula, I want to show that this sum, which I write in yellow, it is equal to k plus 1 squared. And then now we go back to the body and check for the result. Hopefully it's not very difficult for you because you see it's an identity over there. Coming up next is k squared plus 2k plus 1. By identity is k plus 1 squared and achieves our aim. And then in this body we say, now I prove that pk plus 1 is true. Alright, that's good. Finally, we can see the whole body here. Assume pk is true, and we prove that pk plus 1 is true. According to the principle we mentioned on page 1, and now you come to the fourth body, which is a conclusion. And then finally, you can say Pn is true, or sometimes I write a bit longer. So by the principle of Mi, Pn, the whole statement, is true for all positive integers n. That is, so it will be alright for you to understand all the procedures about Mi here. After studying the procedures of Mi, so your first job will be, you remember this 1, 2, 3, 4 steps, 4 bodies about Mi. And then coming up next, we try to take a look on one more example to see how you can apply Mi to get the result. So here I pick one of the past paper in 2012. And then next, let's take a look on the question. So first of all, we say let Pn be the proposition. So you need not to write down the whole sentence because it's shown in the question. I'll say second part of the question will be when n is 1, and we check for your left hand side. N is 1, basically you are talking about the first term, so it's 1 times 2. And you can also verify from the formula will be put n is 1 times 3 minus 1, which is 2. That means the first term only, which is a 2. While on the right hand side you have a formula, which is 1 squared times 1 plus 1, which is 2 as well. You can say is equal to the left hand side, so that we've got P1 is true as follow. Afterward, then you come to the third body, the most important one. We assume pk is true. For the first time you do a question about Mi, so I suggest you to write down the full statement of pk so that you can use it more directly in your calculation. So as a result, when you assume pk is true, that means 1 times 2, 2 times 5, 3 times 8 up to k and 3k minus 1 is equal to k squared, and then you have k plus 1. Afterward, so maybe I change it in green so that you can read the things carefully. When n comes to k plus 1, and now left hand side becomes 1 and 2, 2 and 5, 3 and 8. So I write down the original last term, which is k and 3k minus 1. Okay, but be careful that when n is k plus 1, that means there will be one more additional term. It's called k plus 1, 3 times k plus 1, and minus 1 afterward. Before you proceed to the next line, I would suggest you in your rough worksheet or on another piece of paper, you write down your aim. Your aim is for for this sum, you want to get k plus 1 square and k plus 1 plus 1, k plus 1 plus 1, that means k plus 2 in the outcome. So that's why we will be focused on this product to get the result accordingly. And then next, going back to the calculation, now you've got, okay, now you have got the following. According to the assumption, the sum from 1 times 2 to k times 3k minus 1 is k squared plus k plus 1. So as a result, for these terms, many terms, it goes to, what is it? Is k squared times k plus 1 already. And you still have one more term called k plus 1 and 3k plus 2 as follow. Normally the question will show you common factor so that you can do the calculation easily. Next, we take out the common factor k plus 1, leaving k squared and 3k plus 2 in the second brackets. And next, so of course we need to do cross method factorization, which gives you k plus 2 and k plus 1. Combining k plus 1 to the format of k plus 1 bracket square, and then it's done. Okay, see that it goes back to our focus that we write at the top right hand corner before. In this case, we find that pk plus 1 is true. By our own work, we prove it, and that's why by the principle of MI, and we say Pn is true for all positive integers n.